So, number one, a skydiver in the spread eagle position opens the parachute. Is the diver accelerated? Yes or no? Which direction? And explain your answer. So I had this discussion with several people. I'm just going to make this a smidge bigger for you. Is the skydiver accelerated? And the answer is?
Yeah.
Yes, absolutely. What do? They slow down. That's the whole point of the parachute, is to slow them down. So the answer is indeed yes. And the question is, which direction? Well, here's the skydiver, and there's the parachute, right? Increasing their surface area. We have a weight force down. With this greater surface area, we have a air resistance, and because they're going so fast, the air resistance is very high, and in fact, the air resistance is quite likely greater than the weight force, which means you have a net force which is up, and the acceleration is also up. Now, many of you didn't like that because you think that acceleration means that they have to be speeding up, but it's not true. Acceleration can mean slowing down. It's any change in both speed and direction. Did we not talk about going around the curve at St. Rose Corner? We talked about that, didn't we? Or was that my grade 12s? Did we talk about that? Yeah, no? Okay, so if you got the car on cruise at 100 and you go around the corner at the St. Rose Corner there, are you accelerating? The answer is yes, but your speed doesn't change, your direction changes. Okay, so acceleration can be a change in speed or direction. So the answer is definitely yes, and the direction is definitely up. Now, I had this discussion with the ladies at the back. A weightlifter lifts a 115 kilogram barbell from the ground. How does the force exerted by the lifter compare with the weight of the barbell? And the answer is it sort of depends. Because if they are accelerating the barbell up, then that means that there has to be a net force and it's up, and then therefore the applied force would have to be greater. But if they're just lifting it at a constant speed, then that means that the net force is 0, and they are the same. Right? How does the force exerted by the lifter compare with the weight of the barbell? It would likely be, I would say likely equal, as long as they're moving it at a constant velocity. Now, Megan, you said they had to be the same because of that equal and opposite stuff, right? Read part B. How does the force exerted by the lifter on the barbell compare with the force exerted by the barbell on the lifter? That Newton's law is two objects, two forces, equal and opposite. This answer here is the same. This is the one, Megan, that you were referring to. Okay? But this one is the force by the lifter compared with the weight. Can you apply more force to something than what it weighs? Is that possible? Absolutely. How would you get things to move if you couldn't do that? As soon as you have to move it from rest, you are accelerating. But this one is equal and opposite. These are tricky questions. Number 3 is one of my favorites. Suppose you put a wooden block against a wall and push horizontally to keep it from falling. Draw a diagram showing the force on the block and the cause of those forces. Pay special attention to the normal force and the weight of the block. Are they in the same direction and are they equal? The easiest one to come up with at the start is gravity. Which way is gravity? Down. Which way is the applied force? To the right in this case, against the wall, right? Now, should I do it like over here, or should I do it like over here? When you say one or the other, it's not really a yes-no question. Should I show it as a away from or up towards? Technically, you're supposed to do it like this. If you drew it like this, I'm not going to get too excited. What would you label that force? That would be the applied force, because the person is pushing it against the wall like this, right? Holding it in place. If they let go, what would happen? It would fall down, right? Okay, so how does that work? If they're pushing against the surface, there is a normal force. Does the normal force always oppose gravity? No. The normal force is in fact perpendicular to the surface. Here's the surface, the black wall here. There's the normal force, perpendicular. So which way is friction? Which way would it move if it could? It would move down, so that means that we have friction this way. Does that make sense, Brody? Yeah, you just saying that? Oh, good. I just want to make sure that I'm explaining it right. Andrew, yeah? Okay. I like that question. So I guess here, pay special attention to the normal force and the weight of the block. Are they in the same direction? Is the normal force and the weight of the block in the same direction? No, they're not. Are they equal? Yes. Normal force and the weight, are they equal? Because if I push harder, I get a greater normal force. Does that have anything to do with the weight? No. In this case, right, the weight force and the normal force are not equal, nor are they opposite. It's not always true. Don't fall into that. I really don't like the word always, because always is dangerous. It means forever, always. There's usually exceptions. Okay, now number 4. Let me just double check my notes here, because I always messed up. Explain why an aluminum ball and a steel ball of similar size and shape drop from the same height reach the ground at the same time. Bit of a trick, right? Because we think that they do not land at the same time. Okay? They should, but they won't, because the heavier one is actually able to push that, push the air out of the way easier, right? The surface area to weight ratio is slightly different. Heavier objects will actually plow through the air, will fall faster. I showed you that when I had the tennis ball and the foam ball, and I stood up there, right, and dropped it. They weren't the same size or shape, though, were they? Right? If you have, someone talked about, I think it was Andrew, it was a baseball and a tennis ball, roughly the same. Tennis ball is lighter, right? It has a lower weight compared to its surface area, and it will actually fall a little bit slower. Can you give me some examples of falling objects for which air resistance cannot be ignored? When can you not ignore air resistance? Feather, piece of paper, flat paper, coffee filters, pretty much anything that is light and large. Right? Anything that's light and large. And it also depends on the height. The higher up you go, the less light it has to be. We showed the foam ball. I only had to go up about 8-9 feet. Right? If I drop a baseball off the Empire State Building, or a penny off the Empire State Building, you saw the video, right? Air resistance takes over. The faster it goes, eventually air resistance will take over. So very few objects can you ignore air resistance. Give some for which air resistance can be ignored. What shape does it have to be for you to ignore air resistance? Very aerodynamic. Things like javelins. They're making golf balls more and more aerodynamic, right? So they go farther to reduce air resistance. Anything where air resistance is really small. Very small objects, streamlined and yet heavy. Spears, arrows, bullets, perhaps. Okay, now number 7 is a hard one. Let me get my notes here. I'm going to do this one mathematically. The value of g on the moon is 1/6 of its value on Earth. Will a ball drop from the same height by an astronaut hit the ground with a smaller or larger speed than on Earth? Same ball, same tennis ball, drop from a certain height on Earth. Same tennis ball on the moon, drop from the same height on the moon. Which will hit the ground with a larger speed, or will they be the same? Can we prove this somehow? Can we work it out? The answer is yes. What would be, how would you do it? Do we know what height it's dropped? Does it matter as long as they're both the same. So how about we just make the displacement 1 meter? In fact, minus 1 meter. And let's work it out. Okay? So on Earth, the acceleration is minus 9.8. On the moon, I'll do it over here. Minus 1, the acceleration is minus 1.6. Hannah, you need to put the phone away. Listen, pay attention, be engaged. You'll learn something. Do I know the average speed? No. Do I know the time? No. What's the formula for V bar? Can I just substitute that in? Can I do that for V bar? This V bar is equal to VI plus VF over 2. Is it still equal to D over T? Sure. Do I know what the VI is equal to? 0. So could I just say VF over 2 is equal, and my displacement is? Do I know what VF is? Because the VI is 0, the VF is the same as the delta V, right? Is it not? This is advanced. There's no doubt about it. What's delta V equal to? A times delta T, right? And what's my acceleration? Minus 9.8 T over 2 is equal to 1 over T, and guess what I just did? I only got one variable left, don't I? Minus 9.8 T squared cross multiply. 1 times 2 is 2. T is the square root of 2 over minus 9. Now, how come I got negative? Is that going to work? I got someone. Do you guys see what the problem is? Is there going to be a problem here? Yeah, can't take square root of a negative, right? What did I do wrong? I did one thing wrong. I probably did it on purpose. Negative 1. Did someone say that? Oh, you did? Good for you, Dad. Which is going to make that negative, right? So the time of fall is going to be 0.45 seconds. So that's how long it's going to take to hit the ground on Earth from 1 meter. Now on the moon, oh, what's going on here? No, it's right there, don't worry. On the moon, is all of this true? All of that logic, is all of that true? Absolutely. The only thing that changes is that number right there. So on the moon, it's going to be square root of minus 2 over minus 1.6. Okay. Not surprising, it's going to take longer for it to fall on the moon because it's not accelerating as fast. But, oh, and here, question.
Yeah, what if you take it up like really high?
Uh-huh.
It will never stop accelerating because there's
No air resistance.
Fall.
You're absolutely right. However, over here, we assumed there was no air resistance, right? We didn't account for air resistance. So you're absolutely right. If you take it really, really high on the moon, it's going to continue to fall faster and faster and faster. It would, if you had an Empire State Building built on the moon and dropped a penny and hit someone in the head, that would kill them. Good point. Now, the question really asks what? The question really asks smaller or larger speed. Right? Smaller or larger speed. Now, this one gets there faster. Does that mean that it doesn't have as much time to speed up? This one takes longer. It must be faster speed, don't you think? How am I going to find that out? How fast is it going when it hits the ground? A equals delta V over delta T. The acceleration here is minus 9.8. My T is 0.45. And my change in velocity is going to be okay. A equals delta V over delta T. Remember, the acceleration is only minus 1.6, so it doesn't accelerate as fast, but it goes for a longer time. And what's that equal to? Slower. Slower on the moon. Now you're probably all sitting there freaking out, worrying, is this going to be on the test? No. Sometimes I'm going to challenge you a little bit. Relax. So that you can exhale. You know what? I'm going to leave out 8 and 9 now. Because I've lost you, I can tell. I'm going to leave out 8 and 9. We'll do them tomorrow.